This is Garrett Keane. In this video, I'm presenting the solution to the integration problem which you see here. This equation is a quotient in which the numerator is the quadratic 6x squared plus 7 times x minus 25, and the denominator is the product of the three linear fractions x minus 1 times x minus 2, x plus 2 times x minus 3. If you multiply out these three linear factors, you will get a cubic equation. That is, the first term will be x to the power of 3. In its present form, it is not possible to integrate this equation directly. The correct partial fraction rule must be applied to transform this quotient into smaller quotients, which can be integrated directly using the methods you have previously applied. Your first task is to choose the appropriate partial fraction rule. In our case, we have three linear factors, so we should choose the second equation in this list. To examine this transformation equation, we have on the left-hand side we have our original quotient, on the right-hand side we have three separate quotients, and we have three arbitrary constants, large a, large b, and large c. The first one here, the first element of this one, or first term in this right-hand equation, is large A over x plus A. The second one is large B over x plus B, and the third one is large C over x plus C. If we apply the integration formula to each one of these, and then take the constants outside the integrals, so we take the A outside in this case, the B outside here, the C outside here, we'll see that we are then able to integrate these equations directly. The integral of 1 over x plus A is the log of x plus A. So we get a times the log of x plus a. The integral of the second term, 1 over x plus b, is the log of x plus b, the natural log of x plus b. So we end up with the large B times the log of x plus b. And here we have c times the log of x plus c. And we also have the arbitrary constant of integration, which we call c1, to differentiate from the other c that we already have. If we look at the equation which we have to solve, you can see it's here. This is the rule we're going to apply, and if we apply this transformation equation to our original example, this is the final equation that we get here. Our next task is to work out the values for A, B, and C, the arbitrary constants. To do that, we need to transform this equation in such a way that we remove the quotients from all the terms. That is, we get rid of the denominator. To do that, we multiply each term, the term here on the left-hand side and the three terms on the right-hand side, by the three factors here, the denominator of the left-hand side. Consider the original equation, left-hand side. If we multiply this by the three factors in the denominator, you can see that the denominator will disappear. The x minus 1 cancels with the x minus 1. The x plus 2 cancels with the x plus 2, and the x minus 3 cancels with the x minus 3. So we're left with the original numerator. So this gives us the first term in our revised equation. So what happens when we multiply the first term on the right-hand side by the three factors? You'll see that the factors, when you multiply by the three factors, you have x minus 1 above and x minus 1 below, so they cancel. And basically, the arbitrary constant A is multiplied by the other two factors. This gives us then the second term in our transformed equation. Now we look at the second term on the right-hand side. You multiply it by the three factors, three linear factors. You can see that x plus 2 is in the numerator and x plus 2 is in the denominator, so they cancel. And the arbitrary constant b is multiplied by x minus 1 and x minus 3. That is the other two factors. So this gives us the third term in our transformed equation. We look at what happens when the final term is multiplied by the three linear factors. There's an x minus 3 above and an x minus 3 below, so they cancel. And the arbitrary constant c is multiplied by the other two linear factors. And that gives us the final equation, which is transformed. And now we will be able to work out the arbitrary constants using this transformed equation. To determine the arbitrary constant A, what we can do, if we examine the equation, we can look and see that the arbitrary constant B and the arbitrary constant C are both multiplied by x minus 1. Therefore, if we can get that term x minus 1 to become 0, then the constants B and C will be multiplied by 0, and therefore they will be eliminated. We can achieve this that if we set x equal to 1, we can then see that if I plug in x equal to 1, you can see that the value is shown here in red, is that if you look at the term over here at B, it's 1 minus 1, so that will go to 0. Therefore, C will go to 0, B will go to 0. And if you go to the arbitrary constant C, you'll see it's multiplied by 1 minus 1, so that will go to 0. Therefore, C will be eliminated. If we work these out, it's 6 times 1 squared gives you 6, plus 7 times 1 is 7, minus 25. That is equal to A times 1 plus 2 gives 3. 1 minus 3 gives minus 2. If we look at the next one, B, 1 minus 1 is 0. 1 minus 3 is minus 2. C is multiplied by 1 minus 1, which is 0. And 1 plus 2 is 3. So you can see all those values are shown on the next line. If we evaluate 6 plus 7 is 13 minus 25, we get minus 12. And 3 times minus 2 is minus 6, so we get minus 6a. B goes to 0, C goes to 0. Therefore, to work out A, we divide across by the minus 12 by minus 6, and that tells us that A is equal to 2. Now the next step is to work out a value for the arbitrary constant B. If we look at the A and C, you can see that both of those are multiplied by x plus 2. They both share the linear factor x plus 2. So if we can get that equal to 0, we can do that by setting x equal to minus 2. So if I plug in x equal to minus 2 into that formula, it's 6 times minus 2 squared plus 7 times minus 2 minus 25 is equal to A times minus 2 plus 2, so that those two, when they're added together, will go to 0. Minus 2 minus 3 will give minus 5. B is minus 2 minus 1 will give us minus 3. And minus 2 minus 3 will give us minus 5 when you add those together. And C gives us minus 2 minus 1, which is minus 3, and minus 2 plus 2, which is 0. So you can see, if we go from left to right, we have 6 times minus 2 squared is 4, 6 fours are 24. 7 times minus 2 is minus 14, and we have bring down our minus 25. That is equal to A times 0 multiplied by minus 5, plus B times minus 3 by minus 5, plus C times minus 3 times 0. So you can see here that A and C will be eliminated because they're both multiplied by 0. If we work out the value on the left-hand side here, that will evaluate to minus 15, and minus 3 times minus 5 will give us plus 15 times B. So to work out B, we divide across by 15, and that tells us that B is equal to minus 1. So our next task is to work out the arbitrary constant C. If you look at the arbitrary constants A and B, you'll see that they both share the linear factor x minus 3. So if we put in x is equal to plus 3, you can see that both of those linear factors will go to 0. You can see here that once again plus 3 is put in, shown in red. So 6 times 3 squared plus 7 times 3 minus 25 is equal to A times 3 plus 2, which is 5, multiplied by 3 minus 3, which is 0. So A will go to 0. Plus B multiplied by 3 minus 1 gives you 2. Multiplied by 3 minus 3 gives you 0. So B will go to 0 because it's multiplied by 0. Plus C times 3 minus 1 will give 2. 3 plus 2 will give 5. So you can see these values are shown here. 6 times 3 squared is 9, 9 sixes are 54, plus 7 times 3 give you 21, minus 25 is equal to A times 5 times 0, as we said, a goes to 0. B times 2 times 0, so b will go to 0. And c times 2 times 5, so the coefficient of c will be equal to 10. So when you add up 55 plus 21 minus 25, you get 50. And on the right-hand side, we have 10 times c, so we divide across by the 10, and that tells us that c is equal to 5. So if we go back to our original equation, we transformed it into our three separate quotients. Our next task is to substitute in the values of the arbitrary constants which we have just evaluated. A is equal to 2, B is equal to minus 1, and C is equal to 5. So if you substitute those values in, we get this expression here, and we bring the b, the minus outside for the minus 1 here for the second on the second term on the right hand side. So we get minus the integral of 1 over x plus 2. And if we go ahead and integrate those functions, we get 2 times the log of x minus 1 minus the log of x plus 2 plus 5 times the log of x minus 3 plus the constant of integration. We can choose to leave the answer like this, or else we can transform it into a single term by applying the rules of logarithmic rules. We will do that on the next slide. These two rules of logarithmic functions, if we have the log of x multiplied by a constant a, we can say that that is equal to the log of x to the power of a. And the second rule we're going to use is that the log of x plus the log of y is equal to the log of x multiplied by y. So if we come back to the answer which we got, which were three separate terms, we can apply the first rule, and if we do that, this transforms into 2 times the log of x minus 1 is equal to log of x minus 1 squared, plus the log of x plus 2 to the power of minus 1, because we have a minus in front of it, plus the log of x minus 3 to the power of 5. So we apply the first rule to each term. The next thing we're going to do is apply the second rule. What this enables us to do is if we apply the log of x plus the log of y to the first two, we get the log of x minus 1 squared times the log of x plus 2 to the minus 1. And then if we apply that to the next one, we get the full product, the log of x minus 1 squared plus log of x plus 2 to the minus 1 multiplied by the log of x minus 3 to the power of 5. The last thing we need to do is we have the middle term is to the power of minus 1, so we can bring that underneath, and our final answer is equal to log of x minus 1 squared times x minus 3 to the power of 5 divided by x plus 2. So we transform the three separate logarithmic functions into a single logarithmic function. This gives the final answer for this particular problem. Thank you for listening.